Class is going to be in English. Why? Well, you can ask somebody else, not me. I'm sorry. Everybody here speaks Hebrew?
No, there's foreign exchange students.
I know, yeah. So except them. So the class is going to be in English. One of the tutorials is going to be also in English. The other two are in Hebrew. Well, let's start.
Are we supposed to ask questions?
Alright, so you can ask questions in any language that you like. I prefer English, but it's up to you. If you prefer to ask in Hebrew, I will translate the question to everybody, right? But it's completely up to you. I will answer in English. Right, so I don't really know why, but the department asked me to read your names and sign attendance. Don't worry, if you're not here or at home, it's also fine. I don't really care who comes or who not. It's completely up to you, but the department is really worried people getting lost. So we have 94 names to cover. Let's start. So, please respond. Even if you're at home, open up your mic and respond. Right? Okay. Avitan Shai. Or Partush. Ahmed Muhammad. Shalom. Argawi Yair Asher. Elitzur Linoy Rachel. Amrusi Shaked. Anesh Idan. Asses Joseph. Arangaoz Ilan. Bodnitsky Neta. Boronovsky Reut. Bachar Gil. Baron Avishai. Gaon Eden. גונן אורי, גורוביץ' בועז חן, זה כולם ששמעו שעכשיו עם חישונות ונכנסים? כן. הבנתי. גז אור, גרוס אחיה, גרוס רונית, גריינזייד איתן, גרינזייד, סליחה. תדע גם את השם שלי, אף אחד לא קורא נכון. דל אריאל יוסף, דה בחלב, דגה איתי, דנציגר בת חן, דקל אראל, דרור תמר. We covered one quarter. הורוביץ ענת.
Is it necessary?
Yes. Don't worry, it's going to happen only this once, and I won't accept any other request from the department. Ale Vital, Hendin Yinon, Weber Yitzchak, Wolfius Daniel, Weisbord Dimitri, וינוקור מיטל מילי. צריך להגיד שלום. הבנתי.
תחצור אחת על המחשב.
בסדר. וולך דורון. ונטורה מתן. ורסנו גיא. ורסנו יובל. זילברשטיין חנה אמונה. זלבסט מרגריטה. חווה. בוא, מעולה. חווה זיו, חווה. חדד ינון גד. שלום. חוכלייב סוויטוסלב. חמדה מריה. טיקוצקי איתן. תמיר ארז. פה, בבית, כן? מעולה. תמיר ארז. טרוב יניב. ידבב יובל. יחזקאל אריאל, יחיאלי תומר, יעקביאן רום, ישראל משה,
כן.
כהן הילה, כהן יאיר, כהן סידני, לוי הילה, לוי עומר, מה שוונגר. Are you there?
Yeah, I'm here.
Great. מילשטיין, חנה מרים, מאודר רונאל, מפר גדינה,
כן, פה.
מעולה. משען סגי, נגר לוי, ברק, סבוראי להב, סלם יובל פה, סלע גל, עובדיה דוד מנשה, יוסף יבגני, פינקוס גיא, פלינט נוגה, פרסה איתי, פרסקי דביר יעקב, צברי איתי, צוברי אלעד, לא נפלא, צירולניקוב אליהו, צ'אנג קאו. Are you there? קייטאי ג'אנג, קאווה אביב. Oh, what is your name? Cow. All right. Chang Cow. Great. Kave Aviv. Kolodny Snir. Kon Shachar. Klein Itai. Kalinsky Yonatan. Kravets Anna. כאן. ריבקין שי. רפאלי אור. We almost done. רפאלי יאיר חיים. רצון בן. שעה לינגיו. שעה לינגיו. Here. Great. Hi. Show, Zoren. Show. Here, great. Scheinberg, Shiri. Scheindorf, Shir. Sheni Yarden. Here, great. Sarel Inon. Alright, whoever arrived after I already read their names, please come to me by the end of the lecture and we'll sign
We're
in.
just gonna do this the entire time.
It's the only time we're going to do it for my sake, not for yours. Alright. We are going to talk about statistical physics. After I read this attendance sheet once, I'm not going to repeat it ever again. Alright, so what is statistical physics, why statistical physics, and what we are going to try and achieve during this class. Alright, so three-body problem. So what I mean by three-body problem is when you have three masses, M1, M2, M3, and there is some sort of interaction between those three masses. I repeat myself, if you want to ask questions, don't hesitate. Ask whatever you like. If you have problems speaking in English, ask in ask in Hebrew and I will translate. Alright. Now, why it's so interesting? So, two-body problem you solve in mechanics. Any two-body problem is completely solvable, right? We can always translate everything to the center of mass coordinate, right? And we basically can separate the problem of two bodies to two problems of one bodies. And one body problem, as you solve in analytical mechanics, is always solvable as long as you have energy. And if you can define energy for the system, it is always solvable. I hope you see it. What happens with three bodies? So, actually, it's a huge step. You can think about it. Well, I'm only adding something small. It's another mass into the system. But the complexity it adds, it's a huge step forward. right? So here we have three examples of three-body interactions. Those are gravitational interactions. Those are elastic, so basically three particles that are connected by springs. Okay, and those are also gravitational interactions. Okay? So depends on initial conditions, depends on what type of interactions do you have in your system. You can see that the dynamics is very vast. Okay? You can have something very simple, and you can see those small oscillations. You can see something that actually somehow repeats itself, and sometimes you have this crazy structure, okay, that never repeats itself. And basically, people started to look into those problems since Newton, and even later. And only by the end of the 19th century, this guy, Henri Poincaré, a French mathematician, he proved that actually this problem is unsolvable in its generality. Moreover, he managed to prove that actually this problem, under specific circumstances, can lead to what we call nowadays as chaos. So what is chaos? Right? So you can think of chaos that you cannot predict anything, and it's exactly related to that. Chaotic system is defined by the following assertion. If you have, for example, a particle or the coordinate of a system in one specific location, and you shift this location by a small or infinitesimal amount, right? So you start it over here, and you say, and you can solve exactly the system for those specific initial conditions. You shift your conditions a little bit, and the trajectory of your system is going to be completely different. Not different a little bit, but vastly different. So the difference between two trajectories that are separated a little bit, you know, those very famous float, like the clapping of a butterfly can create extensive change or modifications. And this is exactly the mathematical assertion. You have very small differences between initial conditions, and you're going to obtain extremely different solutions as time goes by. Basically, it means that since we cannot, and you already studied a little bit of quantum mechanics, we can never exactly determine our initial conditions. So basically, this assertion of Henri Poincaré says you cannot predict anything for sufficient amount of time. Right. What we are going to explore in our class. Okay? So we know, or Poincaré proved, three-body system is unpredictable. We are going to do, instead of saying, well, we study three-body problem, we will study problems that involve 10 to the 23 bodies. Okay? So in some sort of it's a joke, right? You cannot solve three particles, you cannot solve four particles, and you're going to try and claim that you can predict something, make assertions, make speculations about what's going to happen to a system that is vastly complex, right? So here I have a box of yellow and black particles. I shake the box, and I want to say something about the different configurations. Can I? According to Poincaré, it's impossible. Right? Even think about it, when you already study electricity or electromagnetism, you said something about the current, the resistivity, right? But if you really think about the microscopical structure, what electricity is, and what wire is, and what is the flow of electron is, even according to the simplest Drude theory of electric current, is electrons, those blue particles, they are flowing through material, and in the material we have atoms. Those atoms are constantly scattering everything around, right? There is created some sort of a chaotic motion, because this particle sometimes is scattered backwards and sometimes is scattered forwards, and you cannot really predict anything. But still, you have some sort of a theory about electricity. So how we achieve this, right? So this is not a class about nothing, right? It's a class about something, and it's a class about how you can treat a large system with huge number of constituents when you do not know to solve exactly even small systems, but somehow we are capable of saying things about large systems with huge number of particles. Okay, so the goal or the key is ignorance in some sense. We cannot say anything exactly about the system, right? We cannot say, well, let's forget about all those different particles, we don't care about them. We have to care about all the particles. We cannot simply ignore them, but we have to ignore something. We have to forget something, and this something is that we have basically throw out of the window and forget that it exists is determinism. Okay. We will start to accept that any system, large system, is deterministic. Okay. You can say, well, Stas, but there are Newton laws, and Newton laws are deterministic. Let's forget about quantum physics for a second. Newton laws are deterministic, so everything has to be deterministic. When I'm saying determinism is dead, okay, I'm saying I am incapable to compute anything deterministically. Anything. Okay. So one great example is every morning I'm checking the weather that is going to be today. So I'm opening my phone and I'm saying to Siri, what's going to be the weather today? And she tells me, the weather today is going to be sunny with 30% of precipitation. Right? How she knows, or Google, or whatever company, that it's going to be 30%? In general, we can maybe compute everything and say there is going to be rain in Bar Ilan today or not. And the answer is that we cannot. And those 30%, how they compute, they run huge number or tens of different models with different initial conditions, and then they make statistics. So basically we cannot compute anything for a complex system exactly, but what we are going to learn is how to compute something about those systems, which not exactly, but probabilistic. Okay. So the operating values, terms that we are going to use in this class is probability functions, densities. I hope you had a class about probability because it's a must. We're going to take about average and variance. We're going to talk specifically about the law of large numbers, because only due to this law and the central limit theorem we can actually compute something. Don't worry, we were not going to prove central limit theorem or going to compute exactly some specific probabilities or estimate the sigma value. But it's something that you should be familiar with, right? Even if you failed in my class. Now, after we've come to this knowledge that we are letting go of huge number of parameters, right? We still are capable, by using the statistical law, to compute, predict, and find the behavior of great system, very interesting systems. Sometimes they are physical, like for example this superconductivity and levitation, and we can see how this, or at least start to see both, how this occurs. How water is boiling and it's separating into two phases, water and vapor. Okay? But funny enough, it's not only some physical matter that is described by those statistical laws. Living systems, right? For example, this swarming material, this is a flock of birds that moving like it's a big something clapped together, or jamming, and it can be jamming of humans, jamming of cars, and can be jamming of particles in a dead system. Everything is somehow can be described as in statistical way. I cannot simply say, well, this yellow car is going to do this or that. I'm not even trying to understand what exactly each of the cars is going to do. But I can understand what on total this mass of car is going to perform. Okay, so in our class, we're not going to deal with non-equilibrium statistical mechanics. This is whoever chooses to study this in the next semester or in graduate school. We're going to talk only about equilibrium statistical mechanics, so it's a natural extension of this thermodynamic class that you had last year. So we are not going to have any dynamics, we don't going to have any currents, and everything is going to be stable, or death. Basic physical matter. Sometimes it's going to be exotic. It can produce interesting behavior, but it's going to be something physical without any motion. I want to finalize this introduction to statistical physics by saying that it's a hard class. It's a tough class. Not only here in Bar Ilan, but in any other place where the subject is studied at a good level. This is an introduction from a book. It's a good book, but it's not part of our curriculum. So the book starts as Ludwig Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. Paul Ehrenfest, carrying on the war, died similar in 1933. Now it's our turn to study statistical mechanics. You don't laugh.
Now it's our turn.
Okay. Why it's tough? Well, it's a law of nature in some sense. So this is not to scare you. It is to scare you a little bit, but it's what is happening over the years in this class. So this is the distribution of the grades in the exam, and this is the probability density function. Okay. So eventually everybody passes. Don't worry. But what you see over here is that around half of the class, at least after Moed A, is failing. So this year I will try to encourage you that will modify this distribution and push everybody to this right hand side of this axis. Right. It is important, okay? So this is the grades. You have 11% homework, 25% quiz, which is already scheduled, and sorry?
Again.
Yeah, so the quiz cannot lower your grade, don't worry. And 67 is the final exam. Sorry?
What about the homework?
Homework can lower your grade. Yeah. Now, moreover, there is a very strong correlation between people who do their homework and do not simply copy whatever you passed on your WhatsApp, Telegram channels. Right? It's very important that you will try and solve the problems on your own in your study groups together with your friends and not just simply copy and submit. The homework is going to be graded and we are going to check part of it at least, or we will try to check part of it at least. As I said, there is a strong correlation between who try and study and the final grade. It is almost impossible to postpone all the studying to the last week and say, well, let's study harsh now and we have a marathon, right? It does not work. Okay? You have to study all the semester in order to prepare yourself for the final exam. The exam is not easy, and if you do not work, you don't leave yourself time to soak the material inside you, and then you fail. All right, so this is it. And now we start something about statistical physics. Yuval, how I get it?
את הפודיום, נכנס שם על חיבוי פשוט. היסטוריה וכמה.
Alright. Yes.
יש משהו שמשתנה חוץ מהשמגים, במוכן?
אוקיי.
לאור המלחמה, מבחינת חומר, נראה לי, לא לזה מייל, אבל כבר יתבולו בחומר הזה, וגם מבחינת היחס שלך, גם ברמת המבחן, וגם העניין שחלקנו, לא במלחמה, חלקנו מפומים, חלקנו הכל בסדר, ולא יודע, לא בסדר.
So you distressed by my presentation?
נראה לי פה חצי כיתה, ואני בכל הכיתה.
Okay, so I'll translate. So the question is there anything different this year regarding the material, regarding the quiz, regarding the difficulty of the class, and on how I'm going, me and the course staff is going to treat people who are affected by the situation in Israel. All right, so yes, we have, so difference is the quiz is not going to lower your grade. This is part 1. Some of the material is not going to be presented this year. We don't have enough time. Okay. I already mentioned some of the material, so it's basically parts of thermodynamics, stuff about microcanonical ensemble, derivations of different canonical representations are going to be omitted. And I don't think that we will have time to cover Ginzburg-Landau theory. Okay. That's, I think, well, that's basically about the material. The difficulty of the class is the same material as last year in sense of difficulty. It's hard to understand phase transitions. It's hard to understand what superconductivity is, or what is what is a Debye model and how you solve it. I cannot lower the Debye model is a Debye model. And eventually, if I omit it, you don't know a huge portion about statistical physics. So I have to teach you Debye model. Or the other material. So the level is not going to be lowered. It's just the amount, part of the material are going to be omitted. Difficulty of the exam. Well, we'll talk about the exam when we get there. Right? How we cope with all the people that are affected. Well, you can but I encourage you to come and meet me and the staff and the TAs to discuss the material. The door is always open, and I can spend extra hours to meet you, whatever you like, whenever you like, and that's it. But the level of the class is not going to be lowered. You're going to study the material that we are studying at the same level. People who are having problems due to the situation, we will try and help them as much as we can. So we can postpone the submission of homeworks for people who need, but not on general basis, on a personal basis. Right? Yes?
You said that the quiz is already scheduled?
Yes, it's the 5th week of the semester.
Okay.
So this year the department wants all the quizzes to be scheduled ahead of time. It's going to be on the department hours on Wednesday, I think. I don't remember the exact date. Okay. Any other questions? Don't worry, don't be so upset. It's going to be fun, hopefully. You're not going to die. And I can promise you this. People who are going to study the whole semester, do their homework, and we can postpone the submission of the homework, and we can introduce additional classes. So for example, who are going into mobilized into the military service right now and don't want to listen to my recordings over Zoom, Meet, or whatever, I can arrange additional classes. All right. The same goes for the TA classes. Right. All right. Yes.
Is there something necessary for advanced courses and research?
No, we will cover everything that you need. I will cover everything that you need for advanced classes. So,
okay.
It is a funny situation a little bit, but statistical physics in Bar-Ilan is always at a very high level, research-based and study-based. So when you finish this class, usually when you go, you will go, for example, to Weizmann or abroad, you will usually cover the same material there, right? Okay. So we will cover everything that you need, even if you're going to Harvard afterwards. Don't go there.
Okay. Will you upload your notes?
So my notes are messy, but if you really want me to upload them, I can upload them. It's hard for me to understand them, but you can have fun.
Okay.
Yes.
Is there a book that the course is following?
Yeah, not a book. There are several books, and you can find the list on Moodle. Okay. Okay. So, any other questions? No. So we're starting now, and we'll repeat whatever you have learned in the class of thermodynamics. So first of all, we start with the first law of thermodynamics. what the first law of thermodynamics basically says is that E, the total internal energy of the system, and if we don't do anything to the system, right, the energy is conserved. So basically the first law of thermodynamics says if you have a system, you close it, you do not heat it up, you do not do anything on the system is not doing anything on the outside world, the energy is going to be conserved. Right? How is it going to be modified? You can modify energy. Right? If you have a system and if you do something to the system, you perform work, then you can modify the system. We will see it in a second. Okay? Additional assertion is this same energy is an extensive quantity. What extensive quantity means? If I have a system and it's divided into two, and here I have E1 and here I have E2, the total energy of the system is the energy of the left hand system E1 plus E2, the energy of the right hand system. Or in general, this extensive means depends linearly on the system size.
We assume the density is constant.
We don't assume anything, we just say that this is it.
What do you mean by the size? Like
the size, so here for example it is x1 and this is x2. Okay, so the total size is x1 plus x2. Now it can go, and you can make it actually not just for two systems, but for any type of a system. So if you have E1, and you have E2, and you have E3, and you have E4, and you have E5, okay? The total energy is E1 plus E2 plus E3 plus E4 plus E5. Now, what actually I am neglecting when I'm writing this equation? I neglected something. What is this something? This something is the interaction energy between the different systems, right? So there is a boundary between E4 and E5. There is a boundary between E1 and E2. When I'm saying that the total energy is just internal energy of this guy plus the internal energy of that guy, there is some interaction energy that I said, well, it's not there, it's zero. It's not zero, but it's very, very, very small compared to E1 and E2. Okay. So we are dealing with macroscopical systems. Okay. So the size of this, although it's much, 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 much bigger than the size of the boundary. Right? So the number of molecules that are sitting in this area are much, 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 much larger than the number of molecules that are on the periphery, okay? And they are contributing to the interaction energy. Macroscopical systems. All our systems are going to be macroscopical, or at least we will treat them macroscopically. Since the number of molecules on the boundary and in the vicinity of the boundary is small compared to the total energy of the system, we can make this assertion. Sometimes it won't work. When it won't work, sometimes the whole system is just a boundary. Then you cannot neglect the interaction energy. Or sometimes the interactions are so long range, for example, gravitational interaction. It's extremely long range interaction, so you cannot simply discriminate some boundary. Okay? So in general, we will say, yeah, an energy is extensive system, but you should remember that it's an assumption, And it's an assumption based on that we neglected the boundary as it is small and there is not a lot of particles there. But sometimes it's not true. How the energy can be modified. So as we know from classical mechanics class, we can perform work, right? And the total change of the energy is usually the amount of work that we performed on the system. Now you learned in thermodynamics there is something else that we can do, right? What we can do, we can heat up the system. Okay? So this is heat. This is external force, work. Work performed on the system. Oh, it depends. Depends. So it's a work performed on the system. Should it be plus or minus?
וזה פועל על המערכת?
So,
זה אמור להיות...
plus. Why not?
אתה יכול להרחיב על זה שנייה?
We will see an example when we treat pressure, and you will see an example where how I define the forces. It depends on how I define the forces. Okay? You will see an example, and this question plus or minus is going to be cleared up there. Okay, now, what is heat? Can heat produce work? So if we have, well, actually it is, it's very simple. So if we have water, okay, and we light a fire under this water, okay, so this is fire. There is vapor, and this vapor is going to rotate a pulley and create a work. So this guy is going to rotate somehow, and this is the work that we can perform by heating up a system. Okay? So basically, this is why heat is entering inside this equation in thermodynamics. We can produce work by transferring heat, by heating something, by lowering the heat, by increasing the heat. Something is going to change, and this is why heat enters to this system. Now, when the energy is modified, what happens? Okay, so how we control the heat, how we control the system. So here we basically can modify or either the heat that is supplied to the system or the work that is performed on the system. Okay, and by doing this, we can change the energy. So, for example, if we take this d omega and I'm going to say we have P external. Answer your question. So if we have a pressure and I write down here that it's an external pressure, and I write down this with a minus sign, multiplied by dV. P external. External pressure. For example, in general, dW is going to be described by some generalized forces multiplied by generalized coordinates. When I say generalized forces, it can be the external pressure. Then the variable that is associated with the pressure is the volume. I can say, well, maybe it's a tension, but Okay? And the coordinate that that's associated with the tension is going to be the length of the system. In general, I want to write this down as F1 dx1 plus F2 dx2 plus Fn dxn. Okay. This is my d omega. How exactly those forces look like, we will see in the future. But you already seen examples of pressure, you've seen examples of tension, and those are the simplest examples that we are going to use. But anything that can be written in the following form as something multiplied by a coordinate, okay, it's basically contributing to my mechanical work of the system, and it's this quantity that can modify the energy. Now it's important to notice that those generalized coordinates are extensive quantities. And these generalized forces are intensive quantities. So this is going to be dependent linearly on the size of the system. This guy is going to be independent of the size of the system, like the pressure. The volume is, of course, depends on how large my system is. The pressure, usually not. Okay. What about the force? Not the force, but what about the heat? What we do with the heat? How we control the heat? So I told you that I can control the mechanical work by specific forces and extending or contracting some coordinates that are related to the system. What about this guy? So yeah, I can light up the fire, I can heat up the water can do something. Right? In general, when we're talking about heat, the way to control it is adiabatic boundary conditions. We basically say, well, if we have a system, okay, this is our system, we can impose something on the boundary of the system. And this something is not going to get any heat to be transferred inside or any heat to be transferred outside. This is my way of controlling the additional parameter that can contribute to modification of the energy. And this is the heat over here. Great, so we explained this guy, okay? We explained that guy. We can control this by external forces and modification of the coordinates. We can control the heat by imposing adiabatic conditions, so we either can lead the heat inside or prevent from the heat getting inside. Is this enough? There should be some additional assertion. What do I mean by additional assertion? Do you remember the problem that I started with? The problem is there are too many degrees of freedom. How many? 10 to the power 23. So if I want to describe the system, as I'm used to describe systems in analytical mechanics, I should provide to you all the positions and all the velocities of all the different molecules that are combining all together the system. Yes?
You wrote vector dx1 is differential. What does it mean? Is differential in volume?
In volume. So for example, okay, so let's, this guy. Thank you. This is X.
Okay.
A generalized coordinate. So this V is gone from over here. Thanks. If you hesitate to ask a question, know this. In the radius of 2 meters around you, there is the probability 1 sitting someone will have exactly the same question. Don't hesitate. Back to the problem. Too many degrees of freedom. We cannot simply describe all of them. The next assertion is that there are simple states of matter. What do you mean by simple? Simple that I do not need 10 to the power 23 degrees of freedom to describe them. Simple is that the system eventually decays, no matter what I do to the system. It eventually will decay to a specific state. Okay? And this state, I call them equilibrium states. Right. So for example, exactly. Equilibrium in Hebrew is shivui mishkal. Now my assertion says that if you take a system, for example, this is time, and this is a magnetization of a chunk of metal. Right? And you do something to this chunk of metal, you apply some magnetic heat to it, you do something. Okay? So this something is maybe oscillating, maybe decaying, maybe going up, but at some point of time, T0, it says, I leave it alone. Right? I'm not going to touch it anymore, and I'm going to see what happens. So what will happen, usually to this chunk of metal, or to the magnetization of this chunk of metal, that will decay, maybe sometimes fast, sometimes slowly, depends on the matter, depends on different conditions, but it will decay eventually to something, to some value. And it's going to be at this value for a very long time. And it doesn't matter for how long I'm going to measure, this M is not going to be modified. As long as I'm not doing anything to the system. I call this state an equilibrium state of the system. In equilibrium state of the system, I can use small number of parameters in order to describe what is actually happening. Okay? In equilibrium, we have only small number of parameters that include the total energy of the system. Total energy of the system somehow defines the equilibrium states. And the extensive coordinates in our class, we assume that any system, place that we treat, if left alone, okay, on its own, eventually will reach an equilibrium state. We are not going to be concerned how fast it's going to reach its equilibrium state. There is an assertion that each equilibrium state, the moment that we define those parameters, like for example the energy and the external coordinates, for example, the size of the system, okay? It doesn't really matter from where we start, it will always converge to the same state, and it's going to live there forever if we're not going to do anything for the system, and we don't care about how it actually reached there. It's not that only we don't care, the system at some point will not care. Okay? This is an assumption, and this assumption is true for the majority of the system, dead physical systems that we know, but actually it's not always true. There are glassy materials, there are active systems when sometimes the equilibrium simply is not reached or on any relevant timescales. There are systems that some internal dynamics prevent the system to reach equilibrium. Right? They are very fascinating and exotic systems, but in our class we are not dealing with them. Right? The only thing that we care is that, yeah, the system can reach equilibrium. How? I don't care. It will reach it eventually, and I'm going to be concerned of what's happening to the system over here. We can, and we will do, take a system at one equilibrium state and modify it somehow and bring it to another equilibrium state. But we won't care how exactly this was performed. Great. So this was the first law of thermodynamics. What is the second law of thermodynamics? We need something else. So this describes the system, this describes the equilibrium. There is some modifications to the energy that I can perform, but how exactly I determine equilibrium? So if I'm going to only deal with equilibrium states, I need to say something how equilibrium is determined. I can do it experimentally, empirically, right? I can say, well, I cannot compute anything, it's complex, right? It have huge number of degrees of freedom. So the only thing that I'm left after all my assertions is to perform experiments, numerical, if you wish, or, well, nobody believes them. So real experiments, leave the system for a while, see where it converges, and that's it. Right? So no place for theory. And this is, of course, not true. Somehow we need another assertion, which of course based on empirical evidence, how those states are defined. Okay? So for this we have the second law of thermodynamics. Now also the first law and the second law you have seen in thermodynamics class. You maybe define it a little bit differently. But believe me, we can translate this language to whatever language you use in your class on thermodynamics. So the second law of thermodynamics. How you define what is equilibrium state? Theoretically, you need a handle to say, I have this set of energies and this set of extensive coordinates. How I define what is equilibrium and what is not. Right? So right now I can only do experiments and wait for a while. And sometimes systems won't converge. Okay, so I wasn't lucky. But I don't want to wait. I want to make predictions, I want to make theory, and I want to understand nature, not just simply watch it. Okay. So what tells me the second law of thermodynamics? It says the following. There is a function S, which is a function of energy and all the different generalized extensive coordinates of the system, which is an extensive, right? And monotonically growing with E. If state B can be reached adiabatically from state A, then SB is larger than SA. So this is the second law of thermodynamics. What do I mean by adiabatically? No heat was transferred to the system or from the system during this process. Yes?
You're talking about generalized coordinates. You're talking about how they were defined in statistics between
Volume, length, number of particles.
Just number of particles means minus number of constraints.
Not exactly. No, you don't. We'll talk about constraints in a second. But it's any coordinate. It's any coordinate that you have inside your system and which is extensive. Any other questions? Yes.
Is it for all state B or for all?
If state B can be reached adiabatically from state A, so you start from equilibrium state A and you can reach another equilibrium state B adiabatically, then this happens.
Okay. Thanks.
Okay. So this is a adiabatic process. Yes?
Don't you also need the system to be isolated in terms of particle flow?
In terms of particle flow. So you will see that this is part of your extensive coordinates. Your extensive coordinates stay exactly the same. Okay? You see, so the only thing that is going to be changed, I told you that if I take the same E and I take the same X, right, and I have different states, state B and I have state A, how I'm going to choose, okay, how I'm going to choose the entropy, we're going to use this assertion in order to define what is the entropy. But I'm not going to modify E, or I'm not going to modify X. Yes?
You said that A is the equilibrium.
Yep. Yeah.
And we get to B after A.
So you start at A and you reach, somehow you can reach B in an adiabatic way. Doesn't really matter how.
But you say after
A is in equilibrium. A is in equilibrium. B is also in equilibrium. If you can start with A and somehow, the only thing that matters is adiabatically, and this is an assumption or the law, right? It's an empirical law. I start from A, I end up at B. The process here adiabatic. This guy over here at B is going to be larger than at A. That's what the law says. Empirical law, law of nature. Okay? Yeah. So enter this guy S. It's the entropy of the system. And at least for now, we will define it for an equilibrium states. It actually can be defined also for non-equilibrium state, but it's not part of this class. All right. So, but what happens? Any other questions? This is a definition of the law. Okay. So you can ask me, Stas, why? And the answer is why the law of Newton, second law of Newton, holds. Well, people have observed it in nature and decided to write it down. Now, of course, nobody have written down in this form, right? So they have written it in different forms. This, it's called axiomatic representation of thermodynamics. It was accepted around 50s of the previous century. Yes?
Is there uniqueness or there is
Great.
more than...
Great. We will come to this point in a bit. Right? In a bit. Okay, so if the process is reversible, then SA is larger than SB. SA equals to SB. What is a reversible process? and what is a irreversible process. So you already have learned in thermodynamics quasi-static process. Okay, what is a quasi-static process? There's a lot of hand waving around this quasi-static process and saying, oh, I'm doing everything very, 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 very slowly. Okay, what it actually means is that at each tiny step, when I'm modifying my parameters of the system is always in equilibrium. So I modify something and I wait. And I modify it again and I still wait. And I modify it again and still wait. This is the quasi-static process. For some materials, it can be achieved, and then the process can be also reversible. Sometimes it cannot. Okay. Now, if two states can be reached by quasi-static process that is reversible, their entropies are exactly the same. Now, let's see if I can actually show it to you. Okay. Yuval? Okay. To stand and we will finish our class. Yes?
Is there a way to predict how slow?
So you need to know more than just the energy of the process. You need to know microscopical properties of the process in order to say something about how fast it will reach equilibrium.
Does it depend on the speed of sound in the material or the heat conductivity?
For example, it's going to depend on a lot of different states. But it depends on the material. So it's not as, there is not a general answer to your question. Okay? So for some materials, heat conductivity is, to know the heat conductivity is enough. For others, it's simply not. There is no general theory of non-equilibrium processes, and there is no general theory of relaxation that is applicable for everything. Okay? But there is a general theory for statistical equilibrium, or almost anything that you want. Okay, so on this part, what do we have? We have an example of a reversible process. So what happens? Something throw cup, it breaks down. Okay? It's never going to be the same cup again. The only way for me to reverse the process is to say, well, I reverse time. Okay? When I reverse time, all the pieces clump up together to the same glass, and it's full again, and it's nice glass. But it doesn't. It never happens in nature, right? So if I break here something, it won't come back to life again, right? We don't see it. But there are physical processes that are reversible and that are quasi-static. Okay. So this is. Let's see. Okay, so this is one process. So what they do, they introduce 3 different dots of dye inside a very, very viscous fluid. Okay, so there is a red dot, there is a blue dot, I think. See? Or it's greenish. So there is a green dot. There should be a. Can you zoom in? You want me to zoom in?
Try click on F.
F?
Maybe increase like the border.
Oh. We will start from. We will speed up it a little bit. Okay. Eventually we'll have to believe me, I think. Okay, there is blue. What? There is a blue one. And what they're going to do they're going to rotate this fluid from the inside. So we have 3 dots. They are centralized, and here they are rotating. It's called a tail flow. And at some point of time, do you know what happens when you mix colors? You get a uniform color of some kind, right? So they're rotating the fluid, and all the different colors eventually uniformize. You can do it at your home if you have viscous enough fluid and this rotation stuff. Okay, at some point of time where everything is uniformized, what they start to do is they reverse the rotation. So this is the parameter of how much I have rotated. Let's see what happens if they reverse everything. Notice that they do it very slowly. Okay? So expectation is, well, I have uniformized flow or fluid. Nothing happens. But, and it's not me reversing the movie. Okay? Okay, so this is a reversible flow. The system was all the time in equilibrium. Right? So all the stories that you've heard about quasi-static process, that it's not actually what it has to do with nature, there's a lot of different processes in nature that can be quasi-static. Yes? So usually, in order to have a reversible process, it has to be quasi-static. In our class, we will very soon forget about reversible and irreversible processes, and all the processes are going to be reversible. Okay? Almost anything that you see in nature, it's irreversible, right? So almost anything that you do is you consume food. It's not reversible. Don't try it. Okay. Almost anything is irreversible. Most of the natural processes are out of equilibrium, but there are processes that are in equilibrium. And if we leave the nature on its own and we somehow have control of the different parameters, we can create those quasi-statical processes. Other questions? No other questions. Okay. So the moment that we have this S, we can say this is a entropy a function. It's a function of the state of the system. What I mean by it's a function of the state of the system, give me E, give me X, and I will have a unique S. Right? You ask me about is S is unique. And my assertion is, part of the second law of thermodynamics, that there is a unique S for given E and given X. Right?
And S0 or something.
What is S0?
Because also to...
No! S0, so the third law of thermodynamics is related to temperature. How do you define temperature? What is temperature? No dynamics in this class. No dynamics. I will tell you something about it. Sorry? It's going to be 0, right? But we haven't defined temperature, so we have to define temperature in a sec. Okay? But the moment we can define temperature, we're going to write the third law of thermodynamics. And the third law of thermodynamics says that the entropy of the system when temperature goes to 0 is 0. Or some specific very constant value. Yeah. It's always, you can, if it's a specific constant value, you can always subtract it. Okay? So this is the entropy of the function. The moment that we say it, we have to understand something. Just a second. All this, what you've been learned about thermodynamics, can be summarized in the following words. Thermodynamics assumes that nature is continuous, all the matter is continuum, and we can describe the different states of the matter as functions that are differentiable that are integrable, okay, and we can apply the laws of calculus to those functions in order to study the behavior of any thermodynamic system. So the moment I will write down some equation, a definition of how I can modify my entropy, how I can modify my energy, some definitions of what the state is, everything else is just some calculus and mathematical operations over the system. Nothing more. Okay? So in the 19th century for physicists it probably was difficult, so the physicists in the 20th century it was already easy, and it's going to be easy for you. Yes, you had a question.
Yeah. I still don't understand why there is unique entropy.
Because I told you so. Because somebody who has defined it told me so. Right? Okay. This is a part of the definition of the entropy and the second one. You have to say that there is a very specific entropy. You have to say.
So why 2s is not...
Why F equals to MA?
No, I'm just asking why 2s is not entropy.
If you double everything by 2.
If I double everything by 2, so you're saying, can I multiply everything by some specific number? Yeah, but what will happen is, because it's extensive, and I don't think that we'll learn it this class, maybe on Tuesday, what actually you're saying to me, if I multiply this by 2, is the same as looking on the system twice this size. We'll prove it. Okay, so all the multiplications that you can have inside your mind is basically the same as looking on larger systems. It's simply changing the scales of your system. And since the system in thermodynamics is assumed to be continuous on any scale, it doesn't matter. Right? It's related to this extensive property of the entropy. Yes. Other questions? No. Great. So if it's a function of the state of the system, right? So we can define it. Yes. Raise your voice up. I cannot hear you. Why? And so it's part of their definition. So the entropy is always defined by the energy, and it's a monotonic function. Why? It's part of the law.
No, he's asking what's a vector.
Why it's not a vector? You're complete. Thanks. All right. So the moment it's a function, I can write a differential of this function, right? So it is ds equals to ds to de for some specific constant x, d plus ds to dx e dot dx. Now what is this guy? Okay. It's a gradient, yeah. So it's ds to dx1 plus ds to dx2 plus ds to dx3 etc. Yes.
To do a gradient like this, all of the coordinates, shouldn't they be of the same dimension?
Of different dimension? What do you mean by of one dimension?
Units.
What do you mean by unit?
If you don't mean that.
No. It's just the way you can think about it as a way to write down in shorthand, a shortened way, exactly this expression. All right. So. What else we have? So we have this equation. We have an additional equation for dE. dq plus f dot dx. Okay. So let's make this f vector. Thank you. Let's make this dq that is a part of reversible process. Okay. So we take this d and we push it inside this guy over here. Okay. So ds equals to ds to de at this part. Q. dq plus ds to dx e plus ds to de over x f dot dx. Now if we take reversible process and we take a diabatic process and also a diabatic process, okay. So what we have for reversible process, ds equals 0. For a diabatic process, dq equals 0. Okay. What we are left with we have 0 on the left hand side, 0 over here. Dx is some general function, so all of whatever we have over here is simply 0. Okay, so we're left with that ds to de to dx e is constant equals to minus ds to de x f. Okay, this is nice, we'll keep it. Now comes another definition. We know that ds to de is always greater than 0. How do we know it? Because I told you so. This is a part of the second law of thermodynamics. S is a monotonically growing function of the energy. Okay, this is great, which implies that dE to ds of x is greater or equals to 0. Okay. Now this guy, dE to ds x, you're going to call temperature. Okay. So we have some general functions S, which is, well, Stas told me something about it, and it's a growing function, but I don't really know what it is, but it's there. Okay? And if I take the derivative of my energy with respect to my entropy, I have something that I call temperature, and temperature is related to some microscopic values. We will discuss it later. Yes?
The down left letter is meant to symbolize what is the constant.
Yes, yes. So, great question. The moment I write something over here, or over here, it means that I take derivative of s with respect to all the different x's while keeping e constant. Okay, so if we have this, and we can use this temperature, so what we have that ds to dx, when e is kept constant, it's minus 1 over the temperature F. Yes. Questions?
Yeah.
Yep.
Why is that true?
Why what true?
ds equals to
This?
Yes.
Plus. It was over here.
Oh, yeah.
Okay.
Okay.
Plus. Yes. From here to here. So, hand grading argument, I can say if you have this guy, you can write it as dE to ds. If it's a full derivative, something like that works also for partial derivatives. So if this is positive, this has to be at least not negative. Because if this is monotonic, can be actually 0. Try to plot the function which is monotonic and then reverse the axis, and you can see that if this is greater than 0, this can actually be 0.
For example, if you have like y equals square of x.
Yep. So I cannot prove greater than 0, but I can prove that it can actually be equal to 0. Okay. So, where are we left with? We have ds equals to ds to de plus ds to dx e dot dx. Okay, now what we know that ds to dx is minus 1 over t f. Okay. And what else do we have? We know that ds over de, it's 1 over temperature. Okay? So we can write ds to dx of E, it is minus 1 over t f, and we know that ds to de x is 1 over temperature, and eventually what we obtain is dE equals to TdS plus f dot dx. What it tells us, first of all, so you can say, Stas, well, it's a nice, very, very nice assertion, but you use something very specific. You use this, and you use this. And how many processes do you have in mind that are reversible and adiabatic? Okay? There's not a lot of them, as you told us, right? But then, you can say the following genius thing. Energy and entropy are what? Are functions of the state. They're defined for equilibrium state. And those are transitions between different equilibrium states. And you don't care. Remember what I told you? You don't care how you reach equilibrium state. So this guy, when defined for equilibrium states, okay, that I'm traveling, I'm modifying my energy, I'm modifying my entropy, I'm modifying my x's such that I'm traveling from one equilibrium state to another equilibrium state, this always holds true. Yes?
That's why they are total differentials.
Yes, exactly. But they can be total differentials only because I defined for equilibrium states. Okay? So this is a general thing now. Moreover, I can say the following thing. What are the natural coordinates of E? Okay? Those are differentials, so the natural coordinates are S, x1, x2, and etc., etc., etc. Those are the natural coordinates, and if I know, or I can solve somehow this equation, if you provide me the generalized forces, you provide the general coordinates, you have a differential equation that you can do something with it and maybe solve it. But this is still not enough. You have only 6 minutes. Why it's not enough? I need something else. I need to say, well, yeah, S is what? Is a function of state, is a function of state. And there is only one specific value of S and E for a given equilibrium, but I haven't told you how to find this value. Right? So we need an additional principle. Okay? An additional principle. So first of all, the third law of thermodynamics, I can already tell you, well, when temperature goes to 0, the entropy goes to 0 as well, or to a constant value. Right? And we can call this constant value 0 if we really like. So this is the third law. It's not so important right now. But we want some operational tool in order to solve this equation. Right? I need some point to hold on and say, well, I know how to find equilibrium because in equilibrium, this and that happens. So what exactly happens at equilibrium? variational principle for entropy. When I was studying in my BA, the best class that I had is analytical mechanics. Why? Because everything is very well defined. You start with a general variational principle that tells you there is a function, and the moment that you find a minimum of this function or a maximum of this function, you can know absolutely everything. Okay? This is a great idea of minimization of some quantity or maximization. The same can be said about thermodynamical system. We can define the function, and if we search for a maximum of this function, specifically of entropy, we can find what our states are and where is equilibrium and how this equilibrium is actually holds. So the general principle, this variational principle for entropy, says the following thing. If we have state A, and in this state A we have some A and X unconstrained variable. For example, this X is if I have two systems, this E1 and E2, and X1 or X is the size of the first system. Okay? For example, think about it, some sort of a boundary over here, and I can push this boundary backwards and forwards, right? And it will modify somehow this state, and it will modify somehow that state, but it's an internal coordinate, and I can somehow modify it. Okay? So I'm starting from a state A, which is equilibrium, okay, and I modify somehow my unconditional constraint, okay, and I arrive to a state B, where I have some energy, and I have X prime, which is I modify my constraint. I somehow push this forward or moved it backwards. So I have B, and it X prime word. So I somehow started from an equilibrium state. I did something to the system. I increased my X or I lowered my X. Then I say, well, let's put a diabatic boundary around everything. Okay? And we know that due to the adiabatic process, the system will eventually have to reach its equilibrium. And I know that its equilibrium is at X. Okay? So if I start from the process, I do something to it by modifying unconstrained variable from X to X prime. Then I put adiabatic constraints on top of all of the system, and I let the system live. Eventually the system has to go to its equilibrium state, which is defined by E and X. Okay? And I know that because this is an adiabatic process, that SA is greater than SB. Any process that can be reached by a adiabatic process, its entropy is larger than the process that you started with. SB is no. So you
get from B to A.
I'm getting to B. So A is larger than SB.
Yeah.
Okay. Everybody fine with the previous definitions? Okay. Give me a minute. Okay. Okay, so what do I know? That SEX attains a maximal value with respect to internal constraints. It means the following. So if I have a system, okay, if I have a system and it has a total constant energy, E, right? Now I can modify the system somehow, but internally, okay, as long as I'm not modifying the total energy of the system, okay, the system will always come back to its equilibrium state. And how it's defined in equilibrium? In equilibrium, we define it as the state with respect to all different axes where this entropy is maximal. So this is a variational principle. I have a quantity, I call it entropy, right? And I know that if I modify something internally inside the system, the only thing that I can do is actually lower the entropy. Anything that I do to the system, as long as I keep my energy constant, and I do it internally, right? I'm not breaking the system and it spreads around in the room. I do something internally to the system, it will always decrease the entropy. So now I have a principle that I can use in order to compute whatever I like. Because I can say, well, for any system, I can modify it a little bit, perturbate it, okay? And I know that whatever I'm doing, the entropy is going to go down. Right? We don't have time, but what I will prove to you on Tuesday is that there is a variational principle for energy. And it's based on the variational principle of entropy. Variational principle for energy. E, S, and X attains a minimal value with respect to internal constraints. Here I keep E constant and I modify something and the energy or the entropy always goes down. No matter what I do, it will always goes down. And here I have S, which is constant. And no matter what I do, the energy will always go up. Any effect that it will have on the system, as long as I'm keeping the entropy constant, it will be always to raise this energy upwards. Okay? So, and this is the principle that we will use later. Well, actually, I'm not sure that this year we will use it later, but energy has to be minimal. Okay? We will use it in the different models. Well, not sure that this year, but the entropy has to be maximal. And we will see it on many, many examples, but not today. Thank you, and sorry for me being late.